In today's class, we will be studying numerical solutions to ordinary differential equations. Now, I'm sure up to the 12th standard you have done certain amount of differential equations. If not, then probably unit 5 or unit 6 you do have some amount of differential equations. Now, let us look at differential equations of first order and first degree. Say dy by dx equal to some function of x and y with initial conditions y at x naught equal to y naught. That means when x is equal to x naught, y is equal to y naught. Now we will study several methods of solving such differential equations. Depending on what category it falls in, you can either solve it by variable separable method or homogeneous differential equations or exact differential equations or linear differential equations, any one of these methods. But if the function does not fall into any of those categories, then it's going to be very difficult to solve this differential equation. Also, sometimes it so happens that this function is not available to us. We only know the values of these derivatives at certain points. So the function is not known, yet we may want to find out the value of the solution to this differential equation at some point. So in all such cases, we will look for an approximate solution to the differential equation. We will be studying three methods in class. We begin with the Taylor series method. I am assuming that somewhere in your calculus class, you have come across Taylor series. Suppose y is the exact solution of this, then by Taylor series expansion about the point x naught, we will get y at x equal to y naught plus x minus x naught into y naught dash plus x minus x naught square into y naught double dash upon 2 factorial plus x minus x naught cube upon 3 factorial, third derivative at x naught. This of course we will denote by y naught in this notation, and so on. I'm not talking anything about the convergence of the series. Then let us just assume that the series expansion is valid. So this is the series expansion for y of x. Now, if you look at this from this equation, we know what is y dash. dy by dx is nothing but y dash. So y dash is given to us. We know what is y naught because initial condition is given to us. We can use this to calculate the value of y dash at x naught. That will give us y naught dash, and then by taking successive derivatives of this, I can find y double dash, y triple dash, y fourth derivative of this, and so on. So depending on the degree of accuracy that is required, this is the fourth derivative. No, this is the third derivative. Depending on the degree of accuracy that is required, I will take that many terms on the right hand side. Right hand side is actually an infinite series, but depending on how many, up to what decimals I want the answer correct, accordingly I will take that many terms from the right hand side. So instead of explaining how to get the derivatives over here, I will explain it in the problem itself. So given dy by dx equal to 1 plus xy and y at 0 equal to 1, this is the initial condition. Find by Taylor series method the value of y at 0.1 correct to 4 decimal places. Let me first write down the Taylor series expansion. We have y at x equal to y naught plus x minus x naught into y naught dash dash plus x minus x naught square upon 2 factorial y naught double dash plus x minus x naught cube upon 3 factorial y naught third derivative and so on. Let me write one more term, x minus x naught raised to 4 upon 4 factorial fourth derivative of y at x naught and so on. So this is the Taylor series expansion. Let us see what are the initial conditions. Initial condition is here when x is x naught and x naught is given to be 0. So when x naught is 0, y at x naught, which we denote by y naught, y at x naught, that means y at 0, this is given to be 1. So y naught is equal to 1. So let me substitute in this equation. Also, I am interested in the value of, okay, let me write this first. So y of x, since x naught is 0, let me put x naught equal to 0 in this expression. I'll get y naught plus x minus 0. So that will be x times y naught dash plus x square by 2 factorial y naught double dash plus x cube by 3 factorial y naught triple dash plus x raised to 4 by 4 factorial fourth derivative of y at x naught and so on. Let's now go after these derivatives. Look at the differential equation that is given. dy by dx, that means y dash is equal to 1 plus xy. Y dash, dy by dx is y dash and that is given to be 1 plus xy. So y dash is equal to 1 plus xy. So let us find out what is y naught dash. Y naught dash means the value of this derivative at x equal to x naught. That will be equal to 1 plus x naught into y naught. And we already know what is x naught and y naught. See, here are the values. X naught is 0. The initial conditions were given to us. X naught is 0. Y naught is equal to 1. So let me substitute. This will be 1 plus 0 into 1. That's equal to 1. So this is y naught dash. Now let's differentiate this again with respect to x. That will give me the second derivative. 1 is a constant, its derivative is 0. Let's use the product rule for this. First function into derivative of the second plus second function into derivative of the first function. So the value of the second derivative at x naught, that means y naught double dash. Y naught double dash will be x naught into y naught dash plus y naught. And x naught is 0. X naught is 0, so this term will become 0. And y naught is equal to 1. So y double dash will also be equal to 1. Then let's go for the third derivative. Third derivative will be first function into derivative of the second plus second function into derivative of the first, and then go to the last term, derivative of this, that is x times y double dash plus 2 times y dash. So value of the third derivative at x naught, y naught triple dash will be, this term will become 0 because x naught is 0, and this will be 2 times y naught dash. Y naught dash is how much? Here. I have written y naught dash is 1. So this will be 2 times 1. And fourth derivative. I am taking up to the fourth derivative because we want the answer correct to 4 decimal places. So I am hoping that by taking up to the fourth derivative, I will get the answer correct up to 4 decimals. Let me again differentiate this first function into derivative of the second plus second function into derivative of the first. Excuse me. And the derivative of this will be y double dash. So this is x times y triple dash plus 3 times y double dash. And therefore, fourth derivative will be equal to x naught is 0. So this term will become 0. This will be 3 times y naught double dash. Y naught double dash is 1. So this will be equal to 3. Let me substitute in that series expansion. Let me substitute in this series expansion the values of the derivatives. So we get y at x. So y at x is equal to y naught. Y naught is 1. Y naught dash is 1. Then x square, 2 factorial is 2. Y naught double dash is 1. I have just now calculated all the values. X cube upon 3 factorial. 3 factorial is 6. Y naught triple dash. Y naught triple dash is 2. Plus x raised to 4 upon 4 factorial, that is 24. Fourth derivative is 3. I will take this only up to the fourth derivative. So approximately y of x should be so much. That means y of x is approximately 1 plus x square by 2 plus x cube by 3 plus x raised to 4 by 8. So this should be the approximate value for y at x. Now there isn't much left to the problem. We are interested in finding the approximate value of y at 0.1. So put x equal to 0.1 in this. Put x equal to 0.1. That means y at 0.1 is approximately equal to y at 0.1. This is approximately 1.105325. So since we want the answer only up to 4 decimal places, you can pick up the first 4 decimal places and you can take the answer as 1.1053. So this should be the value of y at 0.1, correct up to 4 decimal places. So that is one of the methods to solve or to get the value of the solution at a given point close to x naught. Let us take a look at yet another method. This is once again the famous Euler. We have come across this theorem in several variables also. So we will once again start with the differential equation of the first order first degree with initial conditions y at x naught equal to y naught. So we know the value of the function at some point x naught. And a differential equation is given to us. We are interested in finding out the value of the function at some point, say capital M. So we know the value at this point. We are interested in finding out the value of the function y at the point m. The first thing we do is divide this interval x naught m into n equal parts. So we will have points like x1, x2, x3 and so on. xn, second last point will be xn minus 1. So if I want the value of the function at capital M, first we divide this into n equal parts. Let this difference be h. I am dividing it into n subintervals of equal length. So h is x1 minus x0, or I can say that x1 is x0 plus h. Then look at x2. x2 is x1 plus find capital F. Now in Euler's method, we will first find the value of y at x1. Then using this value, we will find the value at x2. Then using this value, we will find the value at x3. So like this, in n steps, we will finally get the value of the function at the required point. So let us see how to go from one point to the next point. Let's come back to the differential equation. The differential equation is dy by dx equal to f of xy, and I know that when x is equal to x0, the value of y at that point is y0. Let me integrate both sides with respect to x. Let me integrate both sides with respect to x in the interval x0 to x1. So I am going to take the integral on both sides over the interval x0 to x1. So that will be dy by dx, integrate with respect to x. So this will be x0 to x1 by, this will be just dy, x0 to x1 f of xy dx. Let me first concentrate only on the left hand side. Integral of 1 dy. Integral of 1 dy is y. But don't forget y is a function of x. And x varies from x0 to x1. Let me leave the right hand side as it is for the moment, because it will be a little difficult to simultaneously understand what's happening on both sides. So let us just concentrate on the left hand side. Integral of 1 dy is y, but let's not forget that y is a function of x. Now let's put the upper limit minus the lower limit value. So if I put the upper limit value, I will get y at x1 minus y at x0. And we will use the notation y1 for the value of y at x1. So y1. Similarly, we use the notation y0 for the value of y at x0. So this works out to be integral x0 to x1 f of xy dx. Now what we are finding is just an approximate solution. So we will be making certain approximations. And the approximation that I am going to make is, I am going to assume that in the interval x0 to x1, this function f of xy is approximately the same as, that means I will assume that in this interval, this function takes the value f of x0 y0 throughout. It is like approximating this function by this constant function in the interval x0 to x1. So I will assume that f of xy is approximately the same as the value of the function at x0 y0. So if I now substitute in this, I will get y1 minus y0 equal to integral x0 to x1 f of x0 y0 dx. So I am assuming that in this interval x0 to x1, the value of the function is approximately equal to f at x0 y0. Now this is a constant, so take it outside the integral. This is the constant, let's take it outside the integral. So we get y1 minus y0 equal to f at x0 y0. Integral of 1 dx. Integral of 1 dx is x. Limits are x0 to x1. And now take the upper limit minus the lower limit. So we get y1 minus y0 equal to f of x0 y0 into x1 minus x1. Let me take y0 to the other side. So I get y1 equal to y0 plus x1 minus x0 into f of So this is how we use the value of the function at x0 point x1. Remember, we have to go up to the end point. Using this now in a similar manner, we get the value of the function at x2 to be y1 plus x2. By the way, I forgot to mention this x1 minus x0. x1 minus x0 is the same as h. x1 minus x0 is the same as h. So in place of this x0 minus x1, I can write h. So the same h will get carried over here because all subintervals have the same length. So this will be h times f of x1. And we continue like this. In the next step, we will get y3 and y4. Finally, our aim is to get yn, which will be equal to yn minus 1 plus h times. And this will be the value of the function at the required point. So this way we go through n steps to get the value of the function at the required point. So that's Euler's method for your. Let's look at an example to understand this method better. Well, we won't be doing the theory again. I'll just be using that iteration formula. dy by dx is x into y. Y at 0 is 1. Estimate y at 0.4 by Euler's method. Let us first write down the initial conditions. When x is x0, that is given to be 0. When x is x0, the value of y at that point is given to be 1. So x0 is 0 and y0 is equal to 1. Now, we want to find out the value of y at 0 is given and we are interested in finding out the value at 0.4. So the value at 0 is given. I want to know the value at 0.4. Now depending on what kind of accuracy you are looking for, accordingly you can subdivide this interval. For convenience, I will subdivide it into 4 parts. As you can see, if you want to divide it into 4 parts, it will have to be 0 to 0.1, 0.1 to 0.2, 0.2 to 0.3 and then 0.4. So my h, the difference from one point to the next is 0.1. My first point x0 is 0. x1 is x0 plus h. You can see from the diagram also. The next point of subdivision is 0.1. Or you can do the calculations algebraically. x1 is x0 plus h. x0 is 0, h is 0.1. So this will be 0.1. Then x2 is x0 plus 2 times h. So that will be 0.2. x3 is 0.3. x4 is 0.4. In successive steps, I get the values of y1, y2, y3, y4. And I am interested in the value of y4. I want the value of the function at 0.4. That means I want y at x4, which I will denote by y4. So let's use Euler's formula. y1 is y0 plus h times f of x0 y0. We know what is y0. y0 is 1. H is 0.1 into value of the function at x0, y0. y0 is 1. Somewhere we must mention very clearly what is the function. So look at the differential equation. The differential equation will always be given in the form dy by dx equal to some function of x and y. So you get that function from your right is x into y. So let us calculate f at 0, 1. In this expression, put x equal to 0, y equal to 1. So we get 1 plus 0.1 into f of 0, 1. F of 0, 1 will be 0 into 1, and that will be 0. So this term is 0. So y1 will be equal to 1. Remember, y1 means y at x1, and x1 is 0.1. So y1, that is y at 0.1 is 1. Now let us calculate y2. Again, by using Euler's formula, we get y2 is equal to y1. y2 is equal to y1 plus h times f of x1, y1. Let me calculate this separately. F of x1, y1. x1 is 0.1 and y1 we have calculated just now in the previous step. y1 is equal to 1. And remember what is f of xy. If you want to write it here again. F of xy is x into y. So f of this into this comma this will be 0.1 into 1, that is 0.1. So let us calculate y2. y2 will be y1. y1 was 1 plus h. h is 0.1. f of x1 y1 is 0.1 and 0.1 into 0.1 is 0.01. So this will be 1.01. So y2 means the value of the function at x2 and x2 is 0.2. y2 is the value of the function at x2, that means 0.2. So y at 0.2 is 1.01. And this needs a little bit of patience for this. Otherwise the method is fairly mechanical. Remember, we have to go up to y4. So let us now write the formula for y3. It works in exactly the same manner. y3 is y2 plus h times f of x2, y2. Let me calculate the function values separately. F of x2, y2. x2 is 0.2 and y2 is 1.01. That will be 0.2 into 1.01 because f of xy is x into y. So this will turn out to be 2, 0, 2, 1, 2, 3. So it should be 0.202. So y3 will be equal to y2. y2 is 1.01 plus h is 0.1 into f of x2 y2. f of x2 y2 is 0.202. I will sum up the calculations here. 1.01. This will be 0.0202. So it will work out to be 1.0302. And y3 is nothing but the value of the function at x3. So this is how we get y3. y3 is 1.0302. And then finally we use the formula of y4 equal to y3 plus h times f of x3 y3. Go ahead and calculate the value of y4. The function is not very complicated. If you have a calculator, so much the better. If not, it's not too complicated. You can actually manually do the calculations. So see if you can get the value of y4. That's the last value that we are looking for. First you can calculate f of x3 y3. x3 is 0.3 and y3 is 1.0302. So use that to first calculate the value of the function at x3 y3 and then substitute. So I hope by now you will have got the values. y4, that is y at 0.4 according to me This is 1.061106. And was it set somewhere in the problem? We want up to so many decimal places. If not, then depending on what kind of a calculator you are using, you will get that many digits. So that's the value of the function at 0.4. The last method that we are going to study in today's class is called Runge-Kutta fourth order method. There is also the second order method. Of course, Runge-Kutta fourth order method gives a slightly more accurate value, but there are more calculations involved. And the second order seems to be left out from the syllabus. So I'll directly go to the fourth order formula and I'll give you the formula directly. So Runge-Kutta fourth order formula. In fact, there's a whole series of formulae that one has to go through. Once you get used to it, the formulae are not difficult to remember. See, we again have a differential equation of the first order first degree with initial conditions y at x0 equal to y0. We are interested in finding out the value of the function at some other point x1. So we want the value of the function at some point x1. We will denote that by y1. I'll directly give you the formula for y1. It is y0 plus 1 upon 6 k1 plus 2k2 plus 2k3 plus k4, where k1 is h times f of x0 y0. H is nothing but x1 minus x0. K2 is h times f of x0 plus h by 2 y0 plus k1 by 2. Then K3 is h times f of x0 plus h by 2, y0 plus k2 by 2. And K4 is h times f of x0 plus h, y0 plus k2. So we won't be doing the theory behind this. Let's directly go to the application. Let's look at a problem based on Runge-Kutta fourth order formula. Use Runge-Kutta fourth order formula to obtain the value of y at 0.2, given that dy by dx is equal to 1 plus y square, and initial condition is y at 0 equal to 0. The initial condition will always be given in the form y at x0 equal to y0. Remember this. So if we compare it with the initial condition given over here, this is x0 and this is y0. So x0 is 0, here of course both are the same, y0 is 0. Also make sure that your differential equation is always in the form dy by dx on one side and everything else to the other side. If not, then you have to transfer some of the terms over there. Then whatever you get on your right hand side is going to be your function. So f of xy is 1 plus y square. Also we are interested in the value of the function at 0 point. We want to find out the value of the function at 0.2. H is x1 minus x0. Difference 0.2. Now all one has to do is to find out K1, K2, K3, K4 first. So look at the formula that are written on the board. Take a look at the formula, copy it down if you need to, and let's start with K1. K1 is h times f of x naught comma y naught. K1 is h times f of x naught comma y naught. H is 0.2 into value of the function at x naught comma y naught. X naught is 0, y naught is 0. So I need f of 0 comma 0. So this is 0.2 into f of x comma y is 1 plus y square. So in this formula put x equal to 0 and y equal to 0. So this is going to be 1 plus 0 square. So this will be 1 into 0.2. So that is 0.2. So K1 is 0.2. K1 is 0.2. Now let's look at the formula for K2. K2 is h times f of x naught plus h by 2 y naught plus K1 by 2. So let's write the formula for K2. K2 is h times f of x naught plus h by 2 comma y naught plus K1 by 2. H is 0.2 into f of x naught is 0, h is 0.2. Simultaneously you can do the calculation, that way you will understand this better. Y naught is 0, K1 is 0.2. So this is 0.2 into f of 0.1 comma 0.1. So now go back to this formula for f of xy, and in this put x equal to 0.1, y equal to 0.1. So we get 0.2 into 1 plus 0.1 square. That means it will be 0.2 into 1.01. So that will be 0.202. This is K. Then we come to K3. K3 is h times f of x naught plus h by 2 comma y naught plus K2 upon 2, because now we know the value of K2, we can substitute. So that will be equal to 0.2 into f of x naught is 0, x naught is 0, h is 0.2, y naught is 0, and K2 is 0.202. So this is 0.2 into f of 0.1 comma 0.101. Again use the formula for f of xy. F of xy is 1 plus y square. So this will be 0.2 into 1 plus square of y, that is 1.01 square. And again I won't be able to orally do this, so I have done the calculations beforehand. This works out to be 0.20204. This is K3. And now let's calculate K4. K4 is on the same side of the board. K4 is h times. Only K1 and K4 are different. H times x naught plus h comma y naught plus K2. Let's substitute once again. H is 0.2, x naught is 0, y naught is 0, and K3 is 0.20204. So that is 0.2 into f of 0.2 comma 0.20204, and f of x comma 1 plus y square. So this will be 1 plus 0.20204 square. So if you check the calculations, you will get K4 to be. And now we have all the values that we require. Here's y1. You just have to substitute in this expression. y1 is the value of the function at x1. So this is the formula for y1. x1, I have taken x1 to be 0.2. So y at 0.2 is y0. y0 is 0 plus 1 upon 6 times k1. k1 is on the other side. I hope you have noted it. 0.2. k2 is 0.202. k3 is 0.20204 plus k4. k4 is 0.208164. I'll give you some time for the calculations. It shouldn't take you very long. I'll give you the answer. It is 0.202707. In the syllabus, there is also the modified Euler's method. But having done 3 of them, you'll at least have enough idea. You can read up that method on your own. So with that, we are done with numerical solutions of ordinary differential equations. In the next class, we'll see an approximate method of solving a system of linear equations, and we'll also see an approximate method for finding the largest eigenvalue and corresponding eigenvector of a matrix. That's all for now.